Bismillah ar-Rahman ar-Rahim. Fluid flow. Flow means quantity over time. The flow could be a liquid. Bismillah ar-Rahman ar-Rahim. Fluid flow. Flow means quantity over time. The flow could be a liquid or gas, and the quantity could be mass or volume. We have two types of flow. We have laminar flow and turbulent flow. Laminar flow, as you can see, it's made of straight lines. There is no eddies or turbulence. It depends upon the viscosity. As you can see, it's noticed by eta, as you can see. And if we make a relationship between flow and the pressure, we'll find it is straight line. And the constant between both of this, of course, is the resistance. We can see this is a device which we can measure the resistance, where we have two sides of flow and there is a constriction. Of course, the pressure drop between the two areas denotes the resistance. On the other hand, the turbulent flow, as we can see, it swirls in eddies, and it creates a line which is not straightforward, but the flow is needs doubling the pressure to yield the required flow. These are the factors that control the laminar flow, called Hagen-Poiseuille equation, where the numerator contains the pi and the pressure difference and the diameter to the power of 4, and in the denominator we find the constant 128, and we find the viscosity and the length. Regarding the turbulent flow, as we can see, it is a complex formula, so we don't have an equation, but we have a correlation. The flow is proportional to the square root of the pressure difference, square root to the inversely proportional to the square root of length, and inversely proportional to the density, which is called rho. The onset of turbulent flow is noted by what we call Reynolds number. Reynolds number in PV, where V is the linear velocity, P is the pressure difference, D is P is the density, and D is the diameter over the viscosity. So whenever I decrease the density, of course, definitely the number will decrease, as you can see from the figure, correlating the flow to the diameter. Of course, flow which is humidified definitely has a much increased critical velocity. That means that there is a 10% higher. In other words, that it gives a less number than 2000 in comparison to the dry gas. Of course, also using air instead of nitrous oxygen has the same yielding figure, which is less than 2000. All these are the factors that correlate the diameter to the flow. And of course, we can correlate the size of the airway to the flow. Whenever we have a tube of 9 and we have a flow of around 9, we are assured that we have a laminar flow. On the other hand, if we increase the flow beyond the 9, of course the flow will be turbulent. Of course, from the importance of this equation, we can of course decrease the respiratory disorder by using helium to decrease the density. As we can see from the figure, this will improve the respiration in such circumstances. Now we come and to talk about tension. Tension is the force per unit length, as you can see from this cylinder. And if we know the Laplace law denotes that the pressure across this cylinder equals the tension of the wall over the radius. You see, T over R. This will give a hint about the pressure. Regarding the sphere, the Laplace law, we double the contour of the due to the double contour of the sphere. The equation is 2T over R. The surface tension present in the alveoli definitely correlates to what we call the collapse of the alveoli, which occurs in the new babies. Of course, if we apply Laplace law in the alveoli and we correlate the pressure to the tension, the radius, definitely the larger the alveoli will distend much than that of the small one, the 200 micrometer to correlated to 100 microns. I'm sorry, at this large alveoli will collapse the small one. So the surfactant lining the surface of the alveoli is capable to either increase the concentration or decrease the concentration to control the surface tension, and at the same time to control making the alveoli not much extended on and not much collapsed. Viscosity is the resistance of the fluid to go through between the layers, and of course we can decrease the viscosity by dextran, and old ages and smokers, of course they have a high level of viscosity. Now we come to flow through Venturi. Venturi is a system where we have a dilatation, then we have a constriction, and we have returned this dilatation to its normal diameter again. The fluid going through has two types of energy. We have what we call the kinetic energy, which is responsible for the velocity, and the potential energy, which is responsible for the pressure. See, so the flow goes through this constriction. Its pressure is being decreased, so this is correlated to the potential energy, so that to keep the energy, the kinetic energy must increase and the velocity increase. So at this constriction we have a low pressure, as you can see from the manometer, and a high velocity. Of course, the energy can be lost by the friction of the fluid through this wall, so we must make this wall smoothly instructed and inclined in a gradually degree. Clinical application of Venturi, as you can see, we have the injector. If we attach a tube through this narrow part where the pressure is decreased, we can cause what we call entrainment, and we can use it as a suction system. On the other hand, we can use it as in the Venturi mask. The Venturi mask is a tube. The tube has a narrowing at its end. This narrowing is capable to increase the velocity of air, and due to the decrease in the pressure and increase in the velocity, it will drag more air around it. So whenever I use 1 liter of oxygen through this tubing, it is capable to drive 9 liters of air around it. Of course, we must put in our mind the back pressure may affect this entrainment ratio. The third application is the nebulizer. As you can see, if this area where the pressure is low is attached to a tubing system with a fluid, this will entrain fluid and will make an atomizer. The Quanta effect is something like the Venturi tube, but it is being branched, and there is no opening in the area where the pressure is decreased and the velocity is increased. But in such circumstances, the fluid going through both branches are not equal, but it's clinging to one of the branches, and this is why infarction can occur in one area, not in the other, when there is a constriction. So suppose this is an area and this is an area, this will be much less affected by that one. Of course, also occurs in the upper airway. We can use this decrease in pressure at this area by using a flow through this narrowing part, where we can direct the fluids upwards and downwards, creating what we call a valve. A valve, of course, we can use it in ventilator. This is what we call fluid logic in ventilators. This is a hint. I hope that I didn't exceed the 15 minutes, and I hope that I succeeded. Very much obliged. Wassalamu alaikum wa rahmatullah.